A Propfan or open-rotor engine is a type of aircraft engine related in concept to both the turboprop and turbofan, but distinct from both. The European Aviation Safety Agency defines it as a turbine engine featuring contra-rotating fan stages not enclosed within a casing. The engine uses a gas turbine to drive an unshrouded contra-rotating propeller like a turboprop, but the design of the propeller itself is more tightly coupled to the turbine design and the two are certified as a single unit. A Propfan is typically designed with a large number of short, highly twisted blades, similar to a turbofan's bypass compressor. For this reason, the Propfan has been variously described as an unducted fan, or an ultra-high bypass turbofan. In technical papers it is described as a small diameter, highly loaded multiple-bladed variable pitch propulsor having swept blades with thin advanced airfoil sections, integrated with a nacelle contour to retard the airflow through the blades thereby reducing compressibility losses and designed to operate with a turbine engine and using a single-stage reduction gear resulting in high performance. The design is intended to offer the speed and performance of a turbofan, with the fuel economy of a turboprop. The Propfan concept was first revealed by Carl Rohrbach and Bruce Metzger of the Hamilton Standard Division of United Technologies in 1975 and was patented by Robert Cornell and Carl Rohrbach of Hamilton Standard in 1979. Later work by General Electric on similar propulsors was done under the name unducted fan, which was a modified turbofan engine, with the fan placed outside the engine nacelle on the same axis as the compressor blades. Limitations and solutions. Propeller blade tip speed limit turboprops have an optimum speed below about 450 miles per hour. The reason is that all propellers lose efficiency at high speed, due to an effect known as wave drag that occurs just below supersonic speeds. This powerful form of drag has a sudden onset, and led to the concept of a sound barrier when it was first encountered in the 1940s. In the case of a propeller, this effect can happen any time the propeller is spun fast enough that the blade tips near the speed of sound, even if the aircraft is motionless on the ground. The most effective way to counteract this problem is by adding more blades to the propeller, allowing it to deliver more power at a lower rotational speed. This is why many World War II fighter designs started with 2 or 3 blade propellers and by the end of the war were using up to 5 blades in some cases as the engines were upgraded and new propellers were needed to more efficiently convert that power. The major downside to this approach is that adding blades makes the propeller harder to balance and maintain and the additional blades cause minor performance penalties. But even with these sorts of measures at some point the forward speed of the plane combined with the rotational speed of the propeller will once again result in wave drag problems. For most aircraft this will occur at speeds over about 450 miles per hour. A method of decreasing wave drag was discovered by German researchers in 1935, sweeping the wing backwards. Today, almost all aircraft designed to fly much above 450 miles per hour use a swept wing. In the 1970s, Hamilton Standard started researching propellers with similar sweep. Since the inside of the propeller is moving slower than the outside, the blade is progressively more swept toward the outside, leading to a curved shape similar to a scimitar, a practice that was first used as far back as 1909, in the Chauvier remake of two-bladed wood propeller used on the Blur copyright Riot 11. Jet aircraft fuel economy Jet aircraft fly faster than conventional propeller-driven aircraft. However, they use more fuel, although for the same fuel consumption a propeller installation produces more thrust. As fuel costs become an increasingly important aspect of commercial aviation, engine designers continue to seek ways to improve aero-engine efficiency. The Propfan concept was developed to deliver 35% better fuel efficiency than contemporary turbofans. In static and air tests on a modified Douglas DC-9, propanes reached a 30% improvement over the OEM turbofans. This efficiency came at a price, as one of the major problems with the Propfan is noise, particularly in an era where aircraft are required to comply with increasingly strict aircraft noise regulations. However, in 2012 GE expects that propanes can meet these noise levels by 2030 when new narrowbody generations from Boeing and Airbus become available. Airlines consistently ask for low noise, and then maximum fuel efficiency. The Hamilton Standard division of United Technologies developed the Propfan concept in the early 1970s. Numerous design variations of the Propfan were tested by Hamilton Standard, in conjunction with NASA in this decade. This testing led to the Propfan Test Assessment Program, where Lockheed Georgia proposed modifying a Gulfstream II to act as in-flight test bed for the Propfan concept, and McDonnell Douglas proposed modifying a DC-9 for the same purpose. NASA chose the Lockheed proposal, where the aircraft had a nacelle added to the left wing, containing a 6,000-horsepower Allison 570 turboprop engine, powering a 9-foot diameter Hamilton Standard SL-7 Propfan. The aircraft, so configured, first flew in March 1987. After an extensive test program, the modifications were removed from the aircraft. General Electric's GE36 unducted fan was a variation on the original Propfan concept, and appears similar to a pusher configuration piston engine. GE's UDF had a novel direct drive arrangement, where the reduction gearbox was replaced by a low-speed 7-stage free turbine. One set of turbine rotors drove the forward set of propellers, while the rear set was driven by the other set of rotors, which rotated in the opposite direction. The turbine had 14 blade rows with 7 stages. Each stage was a pair of counter-rotating rows. Boeing intended to offer GE's pusher UDF engine on the 7J7 platform, and McDonnell Douglas was going to do likewise on their MD-94X airliner. The GE-36 was first flight tested mounted on the No. 3 engine station of a Boeing 727-100 in 1986. McDonnell Douglas developed a proof-of-concept aircraft by modifying its company-owned MD-80. They removed the JT-8D turbofan engine from the left side of the fuselage and replaced it with the GE-36. A number of test flights were conducted, initially out of Mojave, California, which proved the airworthiness, aerodynamic characteristics, and noise signature of the design. Following the initial tests, a first-class cabin was installed inside the aft fuselage, and airline executives were offered the opportunity to experience the UDF-powered aircraft firsthand. The test and marketing flights of the GE-outfitted demonstrator aircraft concluded in 1988, exhibiting a 30% reduction in fuel consumption over turbofan-powered MD-80, full Stage 3 noise compliance, and low levels of interior noise vibration. Due to jet fuel price drops and shifting marketing priorities, Douglas shelved the program the following year. In the 1980s, Allison collaborated with Pratt & Whitney on demonstrating the 578DX Propfan. Unlike the competing GE36 UDF, the 578DX was fairly conventional, having a reduction gearbox between the LP turbine and the Propfan blades. The 578DX was successfully flight tested on a McDonnell Douglas MD-80. However, none of the above projects came to fruition, mainly because of excessive cabin noise and low fuel prices. The Progress D-27 Propfan, developed in the USSR, was designed with the Propfan blades at the front of the engine in a tractor configuration. Two rear-mounted D-27 propanes propelled the Ukrainian Antonov An-180, which was scheduled for a 1995 entry into service. Another Russian Propfan application was the Yakovlev Yak-46. During the 1990s, Antonov also developed the N-70, powered by 4 Progress D-27s in a tractor configuration. The Russian Air Force placed an order for 164 aircraft in 2003, which was subsequently cancelled. However, the N-70 remains available for further investment and production. With increasing prices for jet fuel and the emphasis on engine airframe efficiency to reduce emissions, there is renewed interest in the Propfan concept for jetliners that might come into service beyond the Boeing 787 and Airbus A350XWB. For instance, Airbus has patented aircraft designs with twin rear-mounted counter-rotating propanes. Aircraft with propanes. Antonov An-70. See also, ducted fan, geared turbofan, comparable engines, Europrop TP400, General Electric GE36 UDF, GSCs of NK12, Rolls-Royce RB3011, Pratt & Whitney Allison 578DX, Progress D27, Mitrovic F5, related lists, list of aircraft engines. References. General resources, Propfan propulsion concepts, technology review, design methodology, state-of-the-art designs and future outlook. Raymond Scott Sisek. University of Virginia Department of Mechanical and Aerospace Engineering. Senior Thesis Project. March 25, 2002. External links, Green Sky Thinking, Carbon Credits and the Propfan Comeback. Flight International, June 12, 2007. The EasyJet ECO jet to cut CO2 emissions by 50% by 2015, The Short, Happy Life of the Propfan Air and Space magazine, September 1, 2005, a Euro-OE open rotor a Eurojet engine, Mitrovic F5, open fan thrust augmenter 1947 flight article on an early Propfan.